past, present, and future of cement. The Romans started making concrete more than 2,000 years ago, but it wasn't like the concrete we make today. They had a different formula, which was not as strong as the modern product. The amazing thing is that these ancient buildings are still standing. Roman buildings were durable against the elements, likely due to a key ingredient, volcanic ash. The volcanic ash reacted with lime paste to create a durable mortar that was combined with fist-sized chunks of bricks or volcanic rocks called tuff, and then packed into place to form structures like walls. Modern Portland cement concrete also uses rock aggregate, but with an important difference. The sand and gravel particles are intended to be inert. Any reaction with the cement paste could form gels that expand and crack the concrete. Modern techniques are a major source of carbon pollution, accounting for about 8% of global carbon emissions. The Canadian government is planning to set minimum standards for the carbon footprint of all concrete used in federal construction projects, in an effort to push the industry to curb greenhouse gas emissions. Starting in 2021, Ottawa wants all cement used in federal projects to be an environmental type that produces 10% fewer emissions than regular cement. The production of cement, the key binding agent in concrete, is an emissions-intensive process. The world produces more than 4 billion metric tons of cement annually, accounting for 8% of the global carbon dioxide emissions. The cement production process involves heating limestone to high temperatures, generally using fossil fuels. The heat causes the limestone to break down and release carbon dioxide, which is a second source of emissions. Green cement is a form of cement produced with the help of a carbon-negative manufacturing process. This cement is produced as the final product of a technologically advanced process so that emissions during unit operations are minimalized. Green cement is an eco-friendly product which resolves serious environmental issues and minimizes the carbon footprint of cement production.
Hi, my name is Leah. I'm a PhD student at the University of Ottawa. I study concrete deterioration, so that's part of the civil engineering department. And I have a background in other engineering disciplines. I studied chemical engineering at the University of Waterloo, followed by a master's in mechanical engineering at the University of Waterloo. But ultimately, even though they were different departments, I study kind of chemistry-related aspects of metals and concrete. So another thing that I study is called the alkali aggregate reaction. So when we look at this, we've got the cement paste. So that's the water with cement powder that's hardened, and it's hardened around our aggregates. So that's the rocks inside the concrete. So this isn't an example of damage, but when you get cracks in the aggregate inside the rocks, what it sometimes means is that you have a reaction taking place. So you probably know how a pH of a lemon is around 2, so it's really acidic, and then water has a pH of 7, so it's kind of in the middle. Concrete has a pH of around 13 to 14, so it's the complete opposite end of the scale for pH, and it's very basic. And so this means that it also can hurt you because it's really high pH when it's fresh. But that interacts with the aggregate. So instead of being out in the world at pH 7, it's at pH 13. And that causes a gel to form because of the chemical reaction. And that actually causes expansion inside of the concrete. And so all of the concrete starts to deteriorate. So that's the alkali aggregate reaction. Another thing we have a lot is the freeze-thaw damage. So you can see it in here that you have pieces, it's blurry unfortunately, but pieces of the concrete have fallen off, and that's because concrete is really porous. There's a lot of Like these are aggregates, but you have a lot of moisture that moves through the concrete through the cement. So the cement is kind of like a sponge. It has holes that the water is able to move through. And in the winter when it freezes, it actually expands about 9%. And so when it expands, because the water when it was a liquid filled the holes, it causes the concrete to crack, and that can over time cause parts of the concrete to fall off. And it only goes in so far just because of how the holes are connected, and that's why it slowly chips away from the outside for freeze thaw. As far as other reactions, those are really the big ones. There's some other damage that can happen with chemistry and whatnot, but I don't think we'll probably talk about that today. So you know that there's concrete basically all over the place. Your house might have a concrete foundation, you go over concrete bridges. So we see it all over the place, but unfortunately concrete also causes a lot of greenhouse gases. So the cement, and we can see there's a lot of cement in here, to make the cement so that it can react with water and form a hard solid, it requires you to use a big furnace. And this process, including the chemistry of the process, generates a lot of CO2, which causes greenhouse gases. So to combat that, we work harder to adjust what size of aggregates we use so that they fit together and we need less cement. But we also use something called supplementary cementitious materials. And so what this means is that when you put it in with cement, which causes the pH to be really high, the supplementary cementitious materials in that high pH environment will form a solid as well. So they will, when you put them with water on their own, they aren't able to form a solid and have that reaction. But when you put them in with some cement, they can kind of act the same way as cement. So some of these supplementary cementitious materials that we use come from other processes. So one of the big ones is blast furnace slag, and that comes from a process to make metals. In this process, it also causes a lot of pollution. So that industry has been trying to reduce how much they use the process, which means we've had less of this waste material that we use in concrete. One of the great things about blast furnace slag, I'm pretty sure it's blast furnace slag, about some of the SCMs is that they create smaller holes. Like when you look at a sponge, there's less big pores, so it's a more solid looking sponge of a concrete, and that means that it's less susceptible to things like the freeze thaw problem, and it decreases the chlorides getting to the rebar. So your structures made with the supplementary cementing materials last longer. And when you're looking at greenhouse gases, if your structure lasts longer, then it's longer before you replace it, and it's a complete win as far as decreasing greenhouse gases. So that's really important. Unfortunately, as I said, we're getting lower on these different supplementary cement materials. So scientists are really working hard to make cements that will last longer, that maybe will use less cement and less supplementary cementing materials. So then you also get into something called fillers, which sometimes is actually limestone, which you can use to make cement. And this causes the, like it's just another thing that you pack in that you don't, to take up space in your material without having to have that reaction.